Okay, cool. Okay, so so I'm going to introduce our speaker, David. I'm thrilled, really, to have David here. I messaged him maybe a month or so ago, and he mentioned that he was going to be in Seattle, and intersects perfectly with our environmental AI series. And he kindly offered to swing by and give a talk. This is exactly what we created the environmental AI series for. David is an expert in deep learning and especially ML applied to climate change. He's founded the Climate Change AI, and which has a summer school now, and written the seminal paper, machine learning.
Tackling climate change with machine learning?
Tackling climate change with machine learning.
I'd be happy to call any other paper seminal.
Great, yeah. Sorry. So a bunch of great papers, also theory, deep learning theory papers, and I'm super thrilled to have you here. This is what we're all about, and I'm just thrilled. So thank you.
Thank you so much, Patrick, for inviting me and for all of you for coming. Everybody online, thank you also for coming. Should I stand? Can you still see and hear me? I don't know.
Whatever you want.
Cool. So I have a lot of stuff to talk about, but please feel free to interrupt me if there are any questions at any point. This can be a lot of discussion, and I'll dive right in. We'll see how far we get. I don't think climate change needs much introduction for this audience. We're increasingly seeing the effects of climate change. They're getting increasingly severe as well. And it's worth always bearing in mind as well that climate change serves to exacerbate and perpetuate existing societal inequities and has a disproportionate impact on already disadvantaged communities and geographies, typically. The effects of climate change, however, are felt by everybody right now. We're seeing, enormous heat waves across much of southern U.S., across Europe, and massive flooding in Korea, many other impacts worldwide. It is also important to remember that climate change is not an on-off switch. It is not something where we ever have the luxury of giving up because it's too late, because it's a choice between massively catastrophic impacts and slightly less catastrophic impacts. How bad it gets depends on what we do now. And ultimately, hopefully, we can achieve net zero greenhouse gas emissions by 2050, though this is looking increasingly unlikely. And I keep on looking at 2030 in my calendar and thinking, oh man, that's actually really soon. If we're going to try to bend curves by 2030, that is looking increasingly unlikely, but yeah. There are lots of different actions that we can take. Mitigation, reducing greenhouse gas emissions, and adaptation, resilience to the consequences of the two main families of actions in climate change response, and climate science, which sometimes is folded under adaptation as modeling and understanding the climate. So, how is machine learning relevant to climate action? That paper that Patrick mentioned is an overview paper of lots of different opportunities for machine learning to be a useful tool in climate action. I'm not going to talk about this mostly, but I will talk about some overall themes that we identified in the paper as ways of contextualizing the different roles that machine learning can play, and then use as a framework for the particular examples that I wanted to touch on for my own group's work. Now, these examples are going to come from all different kinds of sectors. I know that many here are focused on climate science, so that's down here in the bottom left. But there are also lots of applications of machine learning, not surprisingly, in everything from power systems to agriculture and forestry to transportation to heavy industry and so on. So the core themes that we see for how machine learning can be relevant to climate action across mitigation, adaptation, and climate science is first, improving operational efficiency. This can mean taking some complex automated system and optimizing it to use less energy, often, So for HVAC systems and heating and cooling systems used in buildings, we're increasingly seeing machine learning-based tools being useful from smart thermostats in personal homes to more complicated controllers for industrial or commercial buildings. And then industrial processes like steel and cement manufacture have also huge opportunities for optimization. Even very slight improvements in a process like steel or cement can have massive emissions impacts because together those sectors account for about 15% of global greenhouse gas emissions. It's worth noting for this first theme that optimizing something does not mean making it have lower emissions. Certainly optimizing something for lower cost does not mean having it reducing emissions necessarily. That can be for a couple of reasons. You can have rebound effects where making something more efficient causes people to use it more. That generally doesn't negate the benefits, but it can reduce the benefits. Depends on the sector. But also optimizing something for cost doesn't necessarily mean optimizing for energy or emissions at all. So for example, if you are increasing the transportation cost in order to save on labor costs, that might actually increase emissions. So just noting that this one can be thorny, but for HVAC and steel and cement manufacture, you probably save money. Gathering information, distilling raw data into useful information is another theme for how machine learning can be relevant. There are a lot of different ways in which this turns up. Oftentimes that is with remote sensing. So remote sensing with satellite imagery or aerial or drone imagery can be useful in, for example, estimating carbon stock, the amount of carbon stored in terrestrial ecosystems. It can be useful in pinpointing deforestation, in quantifying how much communities are at risk from coastal inundation, or many other things. And there are also some NLP examples, though generally speaking fewer, for example, in parsing corporate financial disclosures to pinpoint climate relevant information. The third theme I want to touch on is forecasting. And there are lots of applications of machine learning in working with time series data in the climate context. The examples I want to touch on here are in electricity systems, so both in forecasting supply and demand. So for supply, variable sources of electricity like solar and wind need to be forecasted in order to understand how much power is available in order to meet demand on the electrical grid. And having minute-to-minute forecasts is something that is hard and a good application of machine learning, both from time series data and sometimes from remote sensing imagery of like where the clouds are. Predicting demand is also very valuable. It is also a hard problem. Like currently, one of the ways you predict demand is, the UK just switched over to a deep learning-based system that cut their error rate in half for predicting demand. But before that, as I understand it, they had, people with TD timetables, and they would do things like work out when the television show was going to end, because everybody would get up from the couch and make a cup of tea, and the electric kettles would cause there to be like a 10% bump in electricity consumption across the UK. So it's a difficult problem, and it requires certain amounts of domain information, let's say. Speeding up simulations, which is something that obviously people here work a lot on. Emulating parts of climate models or entire climate models. And grid planning models is a similar situation where you might have some complicated, often physics-based simulation or engineering-based simulation that is time-intensive to run exactly, and so you'd like to emulate it. And then the final theme is in accelerating scientific discovery itself, not replacing experimentation, but augmenting and interplaying with it. So, for example, suggesting materials for use in batteries or solar perovskites for solar energy. And in these cases, the machine learning algorithms are learning from past experiments or from simulations of experiments in order to suggest experimental parameters or actual materials that could be useful in future experiments. Any questions or comments? Okay, so some key considerations overall. It's worth remembering machine learning is not a silver bullet. It's not magically going to solve climate change, unfortunately. both because it's not relevant in every climate change strategy, and even where it is relevant, it's only one piece of the puzzle. If you're working on climate model emulation, you obviously have to be working together with folks from climate science, and the major tools that are going to be used are not just machine learning ones, they're also climate science. High impact applications are not always the flashy ones. The machine learning that you read about in newspapers, I don't need to be saying this, but that's not going to be the impactful, the climate impactful machine learning, typically speaking. Self-driving cars and GPT are probably going to make climate change worse. Happy to talk about that. For different reasons. Interdisciplinary collaboration is really key at every stage, from scoping the right problems. There are so many machine learning people who are really eager to help, but then work on a problem that has not been scoped together with the relevant stakeholders. And so one ends up solving the wrong problem, which is really disappointing because there are a lot of problems that do need solving. So working with collaborators in the relevant domain of application, also stakeholders who are potentially going to be using the technology, which might be different, right? Like researchers are not always the people who are using the technology. It might be, say, you might want to work with researchers in power systems, but also with grid operators if you're working on electrical grids. Incorporating relevant domain information, because you're flying blind if you are not using the insights that people have already learned from working in this space for years. And a lot of what I'm going to be talking about today is ways to incorporate relevant domain information. And then shaping pathways to impact, because obviously publishing a NeurIPS paper is not the end of the road in terms of impact, generally speaking. And then I finally want to touch on equity considerations. There are obviously numerous ways in which both machine learning and various forms of climate action are messed up when it comes to equity. Climate equity and climate justice are lenses through which one can consider both the ways in which climate change exacerbates and reinforces, exacerbates and perpetuates existing systems of inequity and injustice, and also the ways in which climate action can either be used to diminish that effect or to exacerbate it. Some of the ways in which climate equity and climate justice lenses can be considered within the machine learning context include empowering diverse stakeholders to work on relevant problems in this space, which can mean through collaborations, it can mean through funding, it can mean through citations and recognition of the contributions of scholars, and empowering institutions that are outside sort of privileged institutions as well as considering diverse geographies, of course. Selecting and prioritizing problems is another stage where this often fails. So for example, there's a lot of work on predicting wildfires, but less work on predicting locusts or melting glaciers. And it's not coincidence that, Silicon Valley is strongly affected by wildfires, whereas there aren't any locusts in North America. All of these are climate relevant problems. They're all reinforced by climate change, and they're all really worthy of work. They're all serious problems, but we should be directing, VC funding at the locusts, just like we should be directing VC funding at the wildfires. Just remembering that, implicit priorities are sometimes driven by certain stakeholders in certain geographies. And then ensuring data is representative. This can be a problem going a couple of different ways. It can be a problem going the direction of, oh, we don't have data from the global south because there weren't as many resources in certain geographies to collect that data. Or maybe like the global community never thought to put sensors in Africa. And so all the reanalysis data in Africa is really bad. For example, it could also be the other way, where there are bad privacy restrictions in certain geographies. And so we're actually going to use all of our data from underprivileged communities, because those are the communities that we can take data from without having to worry about breaking the law. And so that form of data colonialism is also a problem, sometimes in different problems. So some challenges for machine learning. The challenges for machine learning in climate relevant applications can look different from normal challenges in machine learning or broader challenges that people consider in the field. Some of the common considerations that turn up are incorporating constraints between different variables. For example, constraints that arise from physics and engineering related applications. We know something about the engineering or the physics of the system, and so we have some information about how the variables should behave. This can be helpful in improving accuracy, also in making sure that our answers are not totally bonkers. The next family of challenges that often turn up is distribution shift. For example, that could be if your data is changing across geographies, you're trying to apply it in one geography, which is different from how it's trained. Also time, there's non-stationarity in terms of climate data, for example. As the climate changes, our climate data varies. Limited or imbalanced data, this is really common. Often data is very expensive or time intensive to collect, and it might be imbalanced across different events, say if you're working with extreme events or with rare species in ecology. And then interpretability or accessibility for end users, because if nobody is using these systems or is able to engage with them in a meaningful way, meaningful with respect to those stakeholders, then they aren't useful. So these challenges often take very problem-specific forms. They're not broad solutions necessarily that work across all sectors and applications. And it's worth bearing in mind that high-powered machine learning techniques, at least applied naively, may fail, or they may be overkill. Often these were not designed for problem-specific, for such specific problems. They might be designed for broad benchmark data sets that they're very far removed from what people actually need. And these challenges might not be addressed by such methods. And so what I'm going to be talking about a lot now is thinking about innovation in machine learning, but motivated by structures for incorporating domain information and addressing these domain-specific challenges. And innovation is actually needed at an algorithmic level in order to incorporate such information, because traditionally, machine learning is often very much about learning everything from data. And this is not to say that one shouldn't be learning many things from data, but both because it is not in many cases enough to do that, and also because we have access to a lot more than data, so we can it's both an opportunity and a constraint that we can think of in moving beyond purely data-centric methods. Okay. So the first particular direction that I want to touch on is an example of work that we've been doing in improving operational efficiency. So this is in the domain of power systems, but I'd love to see it being used in some other contexts like climate science, and I think it will be clear why. So the problem here is that balancing the electrical grid requires solving a non-convex optimization problem, and that is called AP-optimal power flow. It is this set of quadratic equations. These are complex valued. It is non-convex, but it is quadratic. And since it's a non-convex optimization problem, exact solutions take a really long time. And so what people do in practice when they are trying to balance the electrical grid is they simplify the problem. They actually linearize it, which is terrible, as you can imagine. You end up with a solution that is very far from optimal. And that, in practice, wastes large amounts of power on the electrical grid, especially if you are working with solar and wind power. So high renewables grids actually have more waste in this regard because you have to solve the problem more times. Now, people have tried to use deep learning for this in the past. And the typical way you would do that is say, I want to optimize this objective function with some penalties for violating the constraints. So you're essentially trading off between the objective function and the constraints. And that is really bad because you get slight infeasibilities that make everything fail. By fail means that the grid goes down, you get a blackout, and people die. So nobody ever wants to use an algorithm that does this.
I think there might be a question.
Yes.
Yeah, Gideon.
Hi. This is probably a very naive question, but there's, I mean, of all of the difficult problems out there, there's amazing algorithms for graph flow, like Ford Fulkerson, or why not just use one of those?
So this is not a max flow min cut problem. It is this is this cannot be written as max flow min cut. You're trying to minimize a quadratic objective function with respect to quadratic constraints. If you go into these, there is actually, these variables are entangled in complex ways because they're literally complex valued.
Oh, so it's because of that last constraint. Otherwise, it would be possible.
Is the kicker. These are the box constraints are linear. They're really easy. It's that last one, but that is the vast majority of the constraints. Is this last one? It's a matrix constraint.
Sure. Okay. Okay.
I'm happy to talk about it offline, but suffice it to say you cannot
Yep.
make it max flow min cut. I mean, max flow min cut is actually it's linear. It's not a quadratic program at all. So
Okay.
both the objective function and the constraints are quadratic here.
Okay. Yeah. Thanks.
No, good question. So what we do is we design a deep learning method that can solve the non-convex optimization problem while enforcing the constraints. So even slight infeasibility is not okay. And this is work related with provability. So the goal is to approximate a mapping from X to Y, where X is the parameters parameterizing your family of optimization problems, and Y is the desired optimum. So you have an objective function and constraints, both parameterized by X. And so what we're going to do is we're going to throw this into a neural network, throw our input X into a neural network, but then we're going to do some non-standard things. We're not actually going to approximate all of our output variables. We're going to approximate some of them. Then we're going to solve for the rest in closed form, or sorry, not in closed form, but without using deep learning. Then we're going to correct for any violations of the inequality constraints, and then we're going to train the entire thing end to end. So let's go through each step. We're going to output a subset of the variables. And the reason for that is that if you have equality constraints here, then you don't actually have full degrees of freedom. If you had 5 equality constraints, then you would be able to solve for 5 of your variables given all the other ones. You have 5 fewer degrees of freedom than if you didn't have the equality constraints. Okay? So you output 5 fewer variables, you solve for those, but how do you solve for them? There isn't necessarily a good closed form way of doing that. So you use a numerical method. In this case, we use Newton-Raphson. That is non-differentiable, but we have a constraint. These are all coming from constraints. And so that since they come from constraints, you can get implicit derivatives for everything by the implicit function theorem. And that enables you to backpropagate when you are going to train this thing. So you output a partial set of variables, complete it to the others, and then you're not done because that's only the equality constraints. You now, the equality constraints are actually the hardest ones because you're trying to stay on this green manifold within your solution space. And you actually want to get to a particular part of the green manifold, which is this subset, which is satisfying the inequality constraints too. How do you do that? Well, you do gradient descent, but you don't do gradient descent on the network. You do gradient descent on the output of the network. You're pushing yourself towards these inequality constraints step by step, and you only need a few steps in practice because you're trying to get within a region. You couldn't do that with equality constraints because you'd be bouncing back and forth across the manifold. But since you're trying to get within a region defined by inequality constraints, you can do that with a few steps of gradient descent. There are a lot of equations here. This is basically just stay on the green manifold while you are getting towards the blue region. So now we have satisfied the equality constraints by definition, and we've moved our output so it satisfies the inequality constraints as well. Now we can train the entire thing end to end. The loss is just minimize the objective function. Notice this is not supervised. You do not need any data points, or at least you don't need the solutions. Why? For the data. You just need the ends. So and then you also have these soft losses, which are saying don't violate the constraints too much. That is just to help the training process. It helps you early on in training. So in practice, how does this work? You can see our algorithm in blue. You can compare it to, this is if you just use the soft loss, so no hard constraints at all, and this violates the constraints significantly. It's very infeasible. Same thing if you use supervised learning, you also violate the constraints. These are various ablations showing that you do need all the components of the method. And here you can compare it to the standard domain-specific solver, high power, which is based on map power, which is what people actually use. And it's 10 times faster than the optimizer, this domain-specific optimizer, while being only slightly less optimal, very, very slightly. And it's actually even faster than 10 times in practice because we've got GPU parallelization. So this is ignoring any parallelization on the GPU. But in practice, deep learning can actually be parallelized a lot more. So it's probably orders of magnitude faster. Okay, any questions? Yes.
What's the this also might be a naive question, but what's the, I guess, the parameter space of the actual optimization problem being solved? Not the deep learning model. I'm just curious, like how this.
So X captures these constraints, so like what the available power is and what the demand is, and it also captures these the A and B variables, which have to do with how much things cost.
Okay. So if it were to scale up where these were like all slightly different values for a bunch of other systems, and you wanted to do that all simultaneously, it's that like.
So like how big a system could you work with?
Yeah.
We were testing this on a standard IEEE like 100 to 150 bus case, which is a not tiny power network. This is what people use in practice to test these kinds of algorithms. We would really like to try it on a much larger network, and we're talking with grid operators to currently to test that. It is scalable. It doesn't like scale really quickly. Yes.
So, but this method seems more general than just this grid problem.
Of course, exactly. That's why I'm bringing it up. So it's a tool for solving non-convex optimization problems, and more broadly, it's a tool for satisfying non-convex constraints or non-linear constraints, which is actually really general. We would love to see this being used in climate science. And we tried for a while to find ways to incorporate this kind of technique into different kinds of problems, but found that in particular in atmospheric science, a lot of the constraints are linearizable. It's possible that there are systems that we did not look at, and we'd really like to find a way to make this be useful in other settings. Specifically in climate science. We also tested it in other domains that aren't ACOPF, and it also works well in those other domains. But I was specifically mentioning the climate modeling or atmospheric science cases. Yeah. Cool. So the next example that I want to touch on is going to touch on both the themes of gathering information and forecasting. And the setting here, the motivation, though again, we'll see it's useful across different domains, is in remote sensing for agriculture. So the problem of agricultural remote sensing is really important since mapping crops and forecasting yield are part of steps that governments take to reduce the risk of food insecurity under climate change. And machine learning is increasingly playing a significant role in processing remote sensing data. However, the data in question are very sparse and they're imbalanced across crops and locations. So you can see in this map how, this is from our partners at NASA Harvest, the blue dots are, do we know if there's a crop there or not? Just some crop. And the orange dots are, we know what kind of crop it is. So the orange dots are the really good data, and there's very little of them. Now, you would like to be able to say, well, I've seen coffee in Brazil and maize in Kenya. Could I work out what coffee in Kenya or maize in Brazil looks like? And so that's what we do. We develop meta-learning algorithms that label crops and predict yield, do other things, while generalizing fast to new locations and new location crop combinations. And so this is work led by my student Gabby, together with Hannah Kerner. Now, the background on meta-learning, really quickly, for those who haven't engaged with it before, meta-learning refers to learning in such a way that the model can quickly adapt to a new task with new data. And in particular, MAML is a really common meta-learning framework in which a neural network is trained specifically to maximize the effectiveness of gradient updates on new tasks. So here you can see that the neural network is being pushed in such a way that a new parameter update you're just trying to choose a new parameter update, which puts you within reach of several optimal parameters settings. So if you go here, because if you saw data from task 1, you'd end up in parameter setting 1. If you saw data from task 2, you'd end up in parameter setting 2. And if you saw data from task 3, you'd end up in parameter setting 3. So you want to be close to good settings of the parameters for lots of different tasks. And your objective is to be quickly adaptable to any new task that you see. As a way of formalizing this. But yeah, that's the quick version of MAML. Now, MAML is a training paradigm, so it can run across network architectures and tasks. And we're going to add a framework on top of MAML that enables you to build in task information to help you generalize better across geographies, across crops, and more broadly across different kinds of task methods. So task-informed meta-learning can be added on top of MAML or other meta-learning frameworks, and it contains two components. The first one is a task encoder. This is an auxiliary neural network in addition to the MAML, the core MAML network. And this incorporates task metadata. In this case, this is lat-long information and crop type. And it uses this to modulate the hidden representations in the meta-learner. So this is the meta-learner, and this neural network has some hidden layers. And in order to learn a task, we're going to incorporate the metadata from the task, like where in the world it is and what kind of crop. We're going to turn that into two vectors, these two vectors which just do an affine transformation on this hidden layer. And you learn these affine transformations that enable you to modulate the hidden representations in the learner. It's a very simple way to incorporate the task metadata, but it's extremely powerful. The naive way to do it, by the way, would be just throw this task metadata as input into the MAML algorithm. That does not work. The second component is forgetfulness. The tasks that the model memorizes or performs perfectly on get dropped from training to enhance generalization. And this is because the data is imbalanced. You don't want it to be overfitting to data from one geography. Incorporate information on geographies and don't overfit to any particular one. So you can see that as compared with these various baselines, and there are actually some more that I didn't throw in here, like MMAML, which is another adaptive MAML, which actually performs worse than MAML in this kind of context. Compared to lots of different baselines, our task-informed meta-learning framework is just vastly better. And it is remarkable that no previous meta-learning algorithms had been able to incorporate this metadata. Again, the naive ways of doing it do not work, but there is a way to incorporate it that significantly boosts performance. And it significantly boosts performance in particular in contexts like Brazil, where there is very minimal data. This is part of the crop harvest data set. It's one of the tasks in the crop harvest data set. And Brazil has very, very little data. Let's look at how increasing the amount of data changes the performance of these various algorithms. So here is the Kenya and the Togo tasks. In Togo, for example, here we're increasing the training set size. So this is how much data you've seen on the new task before you perform well at it. These other algorithms perform pretty well if you've got 1,000 examples, but if you've got 0 examples, then TIML is the only one that performs well. It can do zero-shot generalization because it has some information about what the task is, right? It's seen other geographies. It knows how to generalize roughly across geographies. So it can also do regression. That was a classification task. This is a regression task. It also is state-of-the-art for regression. Now, we've worked on other applications than just agriculture. We are currently working on building HVAC forecasting. So this is understanding the energy use, the energy flow, the temperature, the energy flow within buildings with the HVAC systems. And Kimball is also boosting performance in that context. We've had collaborators use it in the context of carbon flux estimation. It's also been useful there to try to generalize sensor data across geographies there. So really across different data and task modalities, it's really useful, especially in generalizing across geography. Yeah. Questions? I will dive into the next application. There we go. This is also going to be a remote sensing related problem. And here the goal is very broad, try to understand how best to learn remote sensing tasks in general. There are a lot of different remote sensing tasks involved in climate relevant applications, everything from agriculture, which we've already seen, to forest management, and many, many different domains. And the approaches that have previously been used in these kinds of contexts have often used computer vision methods that were developed or even pre-trained using natural images, so things like ImageNet. And that makes sense. We think, oh, that's a satellite image. That means that we should use image-related processing on it. But actually, satellite imagery is very different from other kinds of imagery. The pixels are much more, they represent very far apart things. So 2 pixels in the image might not be very correlated. They might not have very much connection to each other. You also have multiple different kinds of sensory modalities. And we've found is the community has found that state-of-the-art computer vision methods generally don't work very well across remote sensing data. They're not generalizable, they're very computationally intensive, and they are sensor specific too. So if you were trying to work with hyperspectral data, if you train something on ImageNet, that's only RGB. What do you do? So this is work also led by Gabby and Ivan. And what we do here is we leverage the structure of remote sensing imagery specifically. We leverage the multimodal sensors, and we leverage the temporal structure instead of the spatial structure, because while different pixels in the image may not be that correlated, different time points of the same pixel are very, very correlated, and they have a lot of interesting structure. And so what we're going to do is we're going to use a sophisticated architecture. It's going to be a transformer, but it's not going to be a vision transformer. There's no visual processing going on at all. It's taking a single pixel, but a lot of information about that pixel. That pixel has Sentinel-1, Sentinel-2, elevation, precipitation, dynamic world data. So lots of different features, and it's a time series as well. So this is the information that is being thrown in. And this is going to be self-supervised in order to learn meaningful representations. We're going to take that and throw that information with all that structure into a masked autoencoder and ask it to be able to reconstruct anything that you mask out. If you mask out random parts of the data, if you mask out different time points, if you mask out different features. Okay, so it's very robust to the sensory modalities, it's very robust to the temporal structure. And then at inference time, you're going to just try to decode from this representation. Do regression or random forest. You can do something more complicated, but there's no need to. On the encoding for each input pixel. If you had an entire image, you could just have a mixture of experts for all the different pixels. It feels ludicrous. You've thrown out the image structure completely in order to use this other structure, but it turns out that it will work really, really well. So we're going to evaluate Presto. Again, this is self-supervised. It's not trained on these tasks. It's trained on other data. But we're going to evaluate it on these various tasks. Now, these tasks have a varying number of input channels and time steps. Importantly, we're going to try to run Presto on data that doesn't have any temporal structure at all. It's just a single image. And it doesn't have any other channels. It's just RGB. So for example, Eurosat and TreeSat are just basically single image satellite imagery. It's not a time series. It's not lots of features. And it's still going to be, the task is still going to show that Presto is better. We have a variety of training set sizes, everything from very small to sort of large, a variety of task types from segmentation to regression, and a variety of geographies across many different continents. And we're going to find that Presto is state-of-the-art, even though it is significantly smaller, uses significantly less computational power, and doesn't use any of the spatial structure of the image. So here, we've got an image of a lot of trees. We have Sentinel-1 and Sentinel-2 data. This is a single time step. There is no temporal information. But because the Presto encoder was trained using masked autoencoding, it's able to reconstruct all that other information, and it used the temporal structure in order to learn meaningful representations. And so it can actually decode what the species of tree is just from a single image, even though it's only operating on single pixels. So we can compare it on TreeSat to these the other algorithms that have been used on this data set. It's smaller than them, it outperforms them. Similarly on Eurosat, where it beats SatMAE and Scala MAE, which are again state-of-the-art models used on this data set, and it is 1,000 times lighter weight. So very excited about this. It feels like this is just the right way to go about incorporating the structure of remote sensing data, at least in a number of different problems. Any questions about that? So I want to touch on some examples in the context of speeding up simulations, which will perhaps be closest to the work being done in this script, and also includes work being done by Paula. So the goal here is super resolution. So accurate climate predictions are vital to respond to climate change, and also in motivating emissions reduction, because very fine-grained predictions of climate change can help guide local responses, local action. Now, physics-based climate models are very accurate, but as folks here know, computationally intensive. One approach is to emulate climate models or pieces of climate models. Another set of approaches is to take the output of physics-based simulations and increase the resolution. Predictions of physics-based models may be very coarse-grained. They might be a resolution of hundreds of kilometers. That can make local responses hard. So downscaling, aka super resolution, is taking a low resolution prediction and turning it into a high res one. And so I'm going to be talking about two papers, one led by Paula, one led by Qidong Yang, and quickly going through these. So the first paper, which you might have already heard about from Paula, is downscaling with conservation laws. And so the goal here is to incorporate physics-based conservation laws into downscaling algorithms. Conservation laws might apply to mass, energy, momentum, other quantities. And the goal here is that if you have a pixel that is representing some low-res data, then if you were to make it high-res, then the high-res subpixels should sum to or average to the original value in the low-res pixel. And this is useful both in improving accuracy and also enforcing plausibility, because if your end users are going to get some output that doesn't make any sense from the perspective of physics, then they're not likely to buy in very much to your algorithm. And there are various different constraints that we've looked at here. The best performing one is softmax, where we have normalized the subpixel values that we finally output so that they have to sum to the value of the original pixel. This also enforces positivity, which is, as you can imagine, a very good thing for a quantity like water mass, which clearly cannot be negative. So the second thing that I want to talk about here, the second paper, is in downscaling at arbitrary resolution. And here, the context that we're going to need is in FNOs, Fourier neural operators. And so a functional operator, as background, is a map between functions. One can consider an image as a discretization of a function. So the function is basically the infinite resolution version of that image. Now, Fourier neural operators, or FNOs, use a neural network to parameterize a functional operator, and specifically, they work in the Fourier domain to do this. And they've been used very effectively to learn infinite resolution solutions to differential equations like Navier-Stokes. And in particular, the Fourier coefficients work well in these kinds of cases because fluid flow and climate and weather are sort of naturally within the Fourier domain, a little bit more than like pictures of faces. Pictures of faces have sharp boundaries and they are really nasty in the Fourier domain. So we adapt the FNO framework to downscaling, with the input being a low-res image and the output being an infinite res image, like however high-res you want. And the pipeline is to take the input image, throw that through a neural network to process it a bit, and then we're going to do discretization inversion. This is making a piecewise linear function out of the image to basically, to create a function out of an image. And once we have a function, that is this function here, we're going to throw that through a neural operator, and we're going to get another output function. And that output function is our infinite res image. Questions about this framework? Again, taking an image, turning it into a function by just interpolating to create a piecewise linear function. But then that function goes through the Fourier neural operator, and that is what we are after. And both parts of this are learned. Yes.
Could those pieces be like different time steps, for example?
Sorry?
The creative function, could you use like different time steps instead of, I'm just thinking about the interpolation or discretization.
You could definitely imagine this being a like interpolation in time as well as in space. And indeed, we have looked at downscaling in temporal domain as well as in spatial. So we can perform arbitrarily high resolution downscaling. This doesn't mean it's, perfect at doing arbitrarily high resolution, but it means we can do it, which normally machine learning models can't generalize at all to something else. But actually, it turns out it's really, really good. It's really good, not just it's really good in the original thing that it was trained on. So suppose you trained it on 2 times downscaling. It outperforms state of the art on the 2 times downscaling task. But then you ask it to do 4 times downscaling while it was only trained on 2 times, and it actually outperforms state of the art models that were trained on 4 times downscaling. And so the generalization is also state of the art. That's captured here.
Sorry, there was a question.
Yes, question.
It's okay. I'll listen to the results before I ask. Thanks.
Yeah, so the results here, we're comparing it against GANs and CNNs, and the CNNs and the GANs, they were labeled 2 or 4 to indicate whether they were trained on 2 or 4 times downscaling. So for example, this GAN was trained on 2 times downscaling, and so it does very well in the blue task of 2 times downscaling, but it completely fails in 4 times downscaling. But the Fourier neural operator, it was trained on 2 times downscaling, and it actually outperforms all the state of the art on 2 times downscaling, but it also outperforms the state of the art on 4 times downscaling, even the algorithms that were trained on 4 times downscaling. This is this is MSE and this is MAE. Yes, Gideon.
Okay, so I mean, this is a general question that I find myself asking a lot is, do you have any baselines from numerical methods, say at whatever the higher resolution was?
What would it mean to have a baseline? Because the numerical methods are not necessarily going to operate they're not going to operate to downscale. They're going to operate in a different way, right?
Well, you can run the numerical method on whatever resolution you want, right?
But wouldn't the numerical method be to sort of evolve over time rather than to do the super resolution? Like, are you asking about comparison against numerical methods for super resolution?
No. I'm asking about the state, which is, sorry, what is your data is arrow 5?
In this case, yes.
I see. Okay, now I understand.
We're also going to look at Navier-Stokes. And so here we can compare against, again, these are networks that were trained to super resolve Navier-Stokes from a low resolution input. And the idea is that the FNO was actually originally introduced to solve Navier-Stokes. But the way that it was introduced was supposing you have no information at all. This is not that plausible. Like in practice, you can often get a really cheap physics-based approximation. And what we're showing is that you can actually, I don't actually show it here, I realize, I'm sorry, but it vastly outperforms the original FNO because it has access to this low-res version, this cheap low-res version of the solution. And this makes sense, right? Like the paradigm for solving things should be get a cheap low-res version and then downscale, instead of trying to just approximate the thing from scratch, which is what was previously done with the FNO. There's no reason to do that. You can get a better version if you just use the physics solver, but just use it at a really coarse scale.
Okay, so this is maybe a better example then. So let's say your ground truth is Navier-Stokes run at some resolution, say
I'm sorry to cut
1,000.
you off, but I'm gonna have to cut you up and move this to afterwards if that's okay, because I think that
That sounds great.
I think we
Yeah.
only have 10 minutes left in the talk, and I have another whole paper to go through, or 2 papers.
Thank you. Yes. Thanks, Gideon.
No problem.
I'm sorry. I really want to talk about this, and we talked about it a little bit in our meeting before, but I just want to make sure we can close out. So the final theme I want to touch on is accelerating scientific discovery. And here the examples that I want to talk about are in graph neural networks to evaluate electrocatalysts. So currently fossil fuels are required for many settings in difficult to decarbonize industries, like steel or cement, transportation. There isn't really a good way to electrify some of these processes currently, but electrocatalysts are increasingly being developed to allow low carbon electricity to be used in place of fossil fuels or converted into hydrogen or other electrofuels. However, how do we design these electrocatalysts? There's a need for a lot of new ones, and the ways to design them currently involve quantum chemistry simulations using density functional theory. Density functional theory is really slow. It's also not that accurate, but it's really slow. And ML is increasingly being used as an approximation. The state-of-the-art methods use GNNs, but they're still time intensive. And so this limits the utility in evaluating the really large numbers of catalysts you would need to evaluate. Like there are a huge number of different possibilities. So I'm going to quickly summarize mostly the first one of these papers, which we're presenting at ICML next week. But there's also another paper. These are both oriented around making more lightweight, but really effective graph neural networks for these kinds of materials property prediction tasks. And so one of the challenges that people typically face in designing these kinds of GNNs is invariance or equivariance. Now, to some extent, graph neural networks incorporate some portion of this already. But there are ways that you need to incorporate it explicitly if you are going to actually want to be fully invariant or equivariant. So what does this mean? If you have a material like here, ammonia, it doesn't matter what configuration it's in. You can translate it, you can rotate it. You want your property prediction to be the same. Invariance means that your output is preserved under the transformation. Equivariance means that if your input is transformed, then your output gets transformed in the same way. So energy is a scalar quantity. It is invariant. Forces are vector quantities. They are equivariant. If you rotate the input, you rotate the forces. Common solution to build in invariance and equivariance into a neural network is to transform the inputs that don't depend on the spatial orientation. For example, radial basis functions, Bessel basis functions, the Clebsch-Gordon tensor product. I get the sense that some of these things are ways for mathematicians to feel useful. I'm a mathematician, so I can make jokes about mathematicians. They work, but they can be computationally expensive. They can also be hard to understand, and they can be limiting the model architecture. One reason why these graph neural networks get kind of complex and maybe a little bit too complex. We can outsource equivariance to the data instead. And so what we're going to do is we are going to take inspiration from this basic idea that you can make a function equivariant by symmetrizing it, by just averaging over all the possible transformations. However, you can't do that in this case because the number of transformations is infinite. But you can actually do a thing called frame averaging, which is a cheaper way to average. You can choose specific frames to represent the group. I'm not going to get into the representation theory for this. It's not actually that complicated, but I'm happy to talk about it afterwards. And we introduce a frame averaging architecture that provably retains invariance or equivariance, but it allows us to not use any of these like complicated basis functions or tensor products. And so it's a much lighter weight network that is able to learn meaningful representations and actually outperform the more complicated networks. So let's look at the accuracy scalability trade-off. This is the Open Catalyst dataset, which is designed for low carbon energy applications for electrocatalysis. And you can see that our algorithm, which is FANET, is almost as fast as the fastest algorithm, while being more accurate than any of the algorithms. And similarly on QM9 dataset, which is another molecular property prediction dataset, it is here, this is again the error, and this is the relative compute cost. Now it's good to be as far left as possible instead of as far right as possible. Here we are faster than the fastest algorithm while being at the same error rate as all of the other algorithms. This is the SCHNet is the really fast, bad algorithm. So we're like as fast as the fast one and as good as the good one. Now to close out, I do want to note that machine learning does not just have positive impacts on the climate. There are many ways in which machine learning can negatively impact the climate. People often talk about the computational impacts, which are meaningful, and there's been great work that's been done at AI2 to quantify such impacts. These come from computation, like the computation itself, and also come from embodied emissions from hardware. It is, however, worth noting that these are probably dwarfed overall by the applications related impacts. It is worth reminding ourselves that machine learning is used extensively in applications like fossil fuel exploration and extraction. to the tune of $500 billion in additional profit for the oil and gas industry just by 2025. And this is applications that are being led by many of the major research centers and tech companies. So there are those applications. There are also the systemic impacts of applications. Machine learning has enabled online advertising. Online advertising is designed to increase consumption. There aren't really figures on this, but it is fair to assume that there has been a massive amount of increase in consumption thanks to machine learning-based advertising systems. Similarly, in fast fashion. And there are other kinds of system-wide impacts, like autonomous vehicles, which I mentioned before. Self-driving cars are probably going to make climate change worse. And the reason is because they will probably cause people to drive more by making it easier to drive. By implicitly steering technologies in certain ways, for example, implicitly choosing private cars over public transportation. We could also be doing self-driving buses, but we're not really. The technology community is deciding on various kinds of societal impacts implicitly. So it's worth remembering overall that AI for good doesn't mean just adding new good applications of AI on top of business as usual. It also means shaping all applications of AI to be better for society. And that doesn't just mean reducing computation-related impacts, that's good. It also means thinking about what we're using our algorithms for, and thinking about how we can choose exactly how those algorithms get used. I'm going to close by mentioning climate change AI, which Patrick already mentioned. So we are a global nonprofit for catalyzing impactful work at the intersection of climate change and ML. And we have lots of reports, including searchable summaries. You can search by your favorite ML field. You can go to our events. Next one is yet to be announced at NeurIPS, but that is coming up. We have summer school currently taking place. The virtual summer school currently has, I think, 10,000 students. The in-person summer school was very competitive. In person for a few dozen students. I highly encourage applying for either or both. It's designed to be massively scalable, at least in the virtual component. And the funding programs include our innovation grants program, which has given away like $3 million now for research projects that catalyze work across the field. We have a newsletter. If you sign up for one thing, I would recommend signing up for the newsletter because it is a portal to all the other stuff that's happening both at Climate Change AI and across the field, from data sets to papers to job opportunities to funding. And we also run things like webinars and hackathons. Thank you so much for listening, and I think we have a couple of minutes still for questions.
Yeah, thank you so much. People will drop off, but we can hang out here. Thank you so much. That was fantastic. You know, I applied to the competitive side of the.
Yeah, I'm sorry.
I did not. I'm sure I'm not the only one who applied and didn't get in, but yeah, definitely have time for a few questions. I know folks might have to drop off.
We will be scaling up the summer school. We're trying to put different versions of it in different continents. We had 150 countries apply. So yeah, thank you so much. I'll just say one thing, which is that you know, speaking for myself, and I think on behalf of many others, that talk will definitely have a profound impact on how I think about the world, and I think you know, many others here too. So, and my work, and so thank you.